Okay, so hello everyone. My name is Claudia Cuttano, and I am a PhD student in collaboration with the Politecnico di Torino and TU Darmstadt in Germany. So first of all, I would like to thank Voxel for organizing this great event and for giving me the opportunity to present our work. So before going into the details of our work, I would like to spend a few words to describe which is the current landscape in segmentation. So I'm pretty sure that probably most of you already know about segment anything. Segment anything is a foundation model that was released by Meta already 2 years ago, and is a model that has been trained on billions of data. And so we can use this model to perform interactive segmentation, meaning that we can use this model, given an image, to provide a geometric input, for example, a point or a bounding box, and the model will produce the corresponding segmentation mask. So for example, here you have an example where the user can insert, for example, a point, for example, on the frog, and you can see that the model is producing the corresponding mask. So recently, Meta released a new model that is Segment Anything 2 that basically extend the functionality of Segment Anything 1 from images to video. So we have, again, a powerful foundation model trained on billions of data. And what we can do with this model is to perform interactive segmentation not only at image but also at video level. So for example, here there is an example where we have a video, and you can see that we can again insert a geometric prompt. So for example, a point on the cup, you can see that the model again is producing the segmentation mask for the object, but it can also then track the mask across frames in the video. So this is already great, but our question during the last year was, can we go beyond the geometric prompts? So can we go beyond point, bounding boxes and mask? What if we want to prompt segment anything using semantic prompts? And so when we are talking about semantic prompts, for example, we are referring to language. So here there is, for example, a video, and we want the user to be able to type a textual expression. So for example, a cyclist riding a BMX, and we want then the model to be able to reason over the query, localize, segment, and track this object across frames. But then we also are referring to more complex semantic prompts, for example, visual templates. So here there is a particular use case where, for example, we want to just annotate a single example of a boat, and this is our visual template on the left. And then what we want our model to do then is to segment all the boats in unrelated images. So you can see that this has some practical applications, like for example, data annotation. So obviously we are not the first trying to enhance segment anything with semantic prompts. However, what we observe is that what the prior works are doing is actually to just use segment anything as the final step of a pipeline where the real task is solved by an external model. So for example, when we are dealing with language, what is common to do is to use an external visual language model, for example, Lava or Ground in Dino, to produce an embedding that is used to prompt SAM. And the same holds with the visual templates, because what is very common to do is to use an external image encoder that is typically Dino2 to perform feature matching to produce then a point embedding that is used to prompt SAM. So instead, we are going in a real, very different directions, because our question is, can we unlock the semantic understanding directly within the SAM2 model itself? So the point here is that we do not want to use segment anything just as part of a pipeline to solve the last segmentation part, but instead we want to empower segment anything with new capabilities to perform new tasks. And so in the last year, we released two models. One is SAMWISE, that is empowering segment anything with language, and the other one is Sansa, that is empowering segment anything with the capabilities of handling visual template. And so what is particular about our approach is the fact that we are providing a unified framework where we do not fine-tune any of the weights of the original model. So at the end, you obtain a general unified framework where you can still use also the original geometric prompt, but you can also use language or visual template, all without using external models. So in the rest of the presentation, I would like to give you some insight about our model in terms of our technical contribution, but also in terms of results and which are the benefits of our approach. And I would like to start by presenting SAMWISE, that is a model that we recently presented at CVPR. So the first thing that we have to define is which is the task that we are going to solve. So this is a task that in literature is commonly known as referring video object segmentation. So in this task, we aim at segmenting an object in a video given a natural language expression. So you can understand that here we have a lot of challenges, as we can have rich and diverse textual expression requiring different level of reasoning. We can also have to disambiguate among multiple similar objects, and these objects can become hidden or overlapping over time. So what we have seen is that in the literature, the main solution can be divided into approaches. So some operate on short, independent clips in the video, which limit their ability to reason over long-term context, but that allow for streaming processing, while others process the entire video offline, which impairs their applicability in streaming-like scenarios, but has the benefits of having access to the global context of the scene. So in our work, we want to retain the benefits of both the approaches, and in particular, we noticed that Segment Anything 2 already introduced a memory bank that allow for streaming processing while leveraging information from past context. So our question is, can we transfer the tracking and segmentation capabilities of Segment Anything 2 to perform streaming referring video object segmentation? So this seems like a natural next step, but this also entails some not trivial challenges. So first of all, as I was saying before, we have the first challenge that is about text understanding. So Segment Anything only supports geometric prompts like points or boxes and has no native supports for semantic prompts like language. Prior works try to explore how to expand Segment Anything to also operate with language, but they still rely on external large visual language models. Then we have another problem that is temporal modeling. So the fact that in our task, that is RVOS, it's not enough to match the visual appearances of object across frames, as we also need to recognize the object based on how it acts over time. So this means that we have to model the temporal evolution of object, but Segment Anything process frames independently. So you can see that if we have to disambiguate between a person that is running or walking, we cannot look at the video at image level. And finally, we also have discovered that there is a problem in Segment Anything that we denote as tracking bias. So the point here is that Segment Anything is designed to be used in an interactive way. So for example, here I'm showing a video, and you can see that at the beginning, a user can insert the geometric prompt, for example, a point, and the user can insert this point, for example, on the ball and on one of the two shoes of the player. So you can see that the model is producing the segmentation mask for this object and then is tracking these masks over time. However, you can also see that at a certain point, the model incorrectly start tracking also the other shoe of the player. But in that case, you can see that you as a user can assist the model by providing a new prompt, in this case a negative point that can be inserted, for example, on the incorrect shoe, and in this way the model is able to recover its prediction. However, in setting like ours, or setting where we have language, there is not a human in the loop. So if the target object is occluded, ambiguous, or not yet visible, Segment Anything may start tracking an object that only partially matches the text. So for example, here there is a short clip where I ask you to identify which is the surfer that is running on the beach. So I'm pretty sure that you are not sure about which is the correct object. However, if I let you show the entire video, there is a certain point where you as a human are able to detect that there is an object that is more aligned with the text, and so you are able to switch to the correct object. What we note instead is that Segment Anything 2 once it starts tracking an object, is not able to switch when a new object more aligned with the text becomes identifiable. And so we refer to this phenomenon as tracking bias. So in this work, we aim at overcoming all these limitations and making SAM2 wiser by enabling text understanding, temporal modeling, and the ability to correct all these tracking mistakes without any fine-tuning and without relying on external large visual language models. So this is the architecture of SAMWISE. It builds entirely on top of a frozen segment anything 2 and a frozen text encoder, and we just add and train few lightweight dedicated modules. So I don't want to go too deeply into the technical details. However, I want just to give you some insights about our contribution and how our contribution overcome the limitation that I showed you before. So in terms of text understanding, what we did was to expand the prompt encoder of segment anything with a learnable projection that maps the textual embedding into the prompt space. In this way, we let the textual expression directly guide the segmentation process. Then we introduced a novel adapter that is named cross-modal temporal adapter that is inserted at multiple intermediate stages of the feature extraction stage. And with this adapter, what we want to do is to progressively enrich each modality, the visual and textual modality, with the other. In terms of temporal modeling, we model the temporal evolution directly into the feature space inside the cross-modal adapter. In particular, what we observe is that an action typically spans only a localized region of the image. So instead of computing globally, we perform a localized self-attention only across nearby temporally and spatially region. So in this way, we are able to model the temporal evolution of objects while also reducing unnecessary computation. And finally, we also address the tracking bias problem. So the phenomenon where SAM2 may start tracking an object that only partially matches the text and is not able to switch when a new object more aligned with the text becomes identifiable. In particular, what we observe is that the tracking bias is encoded in the memory features that are the features that are biased by past prediction. And what we observe in particular is that if we observe the memoryless features that are the raw features from the image encoder, we are able to understand when these two representations are pointing to different objects. And so we introduce a lightweight module that is the conditional memory encoder that basically compares these two representations, and when the two differs, is able to embed both of them in the memory bank, giving the model the opportunity to balance historical past context with new raw information. So I would like to show this simple example that highlight the challenges that we have in this task and how we overcome them. So here we have a short clip from The Lord of the Rings, where we want to identify the guy who is drinking. And notice that we are processing the video frame by frame in a streaming scenario where we process the frames as they become available. So you can see that at the beginning, it's not clear which is the correct person to segment, as nobody of the two people is performing the action of drinking. However, there is one of the two that is holding the glass more visibly, and so SAMWISE starts tracking this person. Then there is a certain point where you can actually see that the other person is starting performing the action. So SAMWISE is able to detect this situation and is able to switch to the correct person and keeps tracking that person as the action unfolds, even through occlusion, and is also able to recover the prediction after the occlusions. So in terms of numbers, what we have seen is that our learnable projection already enabled the task with a 45% of accuracy on the challenging Mavis dataset, and then each of our technical contribution contribute to the final performance of the model. So overall, SAMWISE is state-of-the-art across all the referring video object segmentation benchmarks. Also, when compared with models based on large visual language model with billions of parameters. So you can see that we are not only outperforming all these methods, but we are also the smallest models available with only 202 million parameters. Moreover, SAMWISE also provides state-of-the-art performance at image level on the referring image segmentation benchmark. And what I think that is interesting is that we obtain all of this by adding and training less than 5 million parameters overall. So SAMWISE consistently outperform all the prior works, both at video and image level, while also being the smallest model available. But what I think that is interesting is the fact that, as I was saying before, we are obviously not the first trying to enhance segment anything with language. But what we did was something very different with respect to the prior works, as we decided to not delegate the visual text alignment to an external VLM, but we proved that it's possible to directly align segment anything with a text encoder. We also did that without disrupting the capability of segment anything to work in a streaming way, meaning that you can use this model in all these scenarios where you do not have access to the entire video. And finally, we obtained the results without fine-tuning any of the weights of the original model. So at the end, you have a unified framework that you can use both with language prompt, but also still with geometric prompt. And so this is a general overview of this model, but I would like to go further on the second model, that is Sansa, that basically extend this idea also to visual template. So I would like to start again by showing you this slide where we had some numbers, because apart from our technical contribution that brings us to the final state-of-the-art performance, what we think is particularly interesting is this number. So the fact that we are able to unlock the task obtaining reasonable performance already just with a projection on top of the feature extraction stage. So this implies that in segment anything, there are semantic structure already present in the feature space. And so segment anything 2 has been traditionally used to perform just simple object tracking, meaning that we have a video, we select an object in the first frame, and then we want to track that specific object across frame. But since we think that there are semantic structure in this model, we ask ourselves, what if we can also solve more semantic tasks, like, for example, few-shot segmentation? So this is the idea. We have, for example, an annotated image of a boat, and then what we want to do is to segment all the boats in unrelated images. So you can see that this has a lot of practical application, especially in the annotation process of large database. So the point here is that we started trying to solve this task in a zero-shot way. So we just tried to test the performance of SAM2 on this task. And we started by selecting simple medical domains where we have images where we have very low semantic similarity and high visual similarity. So you can see here that we have multiple images of lungs. We want just to provide the model with a single annotated example of the lungs, and then we want to segment all the lungs in all the remaining images. And what we found is that surprisingly, SAM2 is working surprisingly well, even also outperforming state-of-the-art approaches. However, we then move to more complex dataset, for example, dataset like Coco or Elvis, where we have high semantic variability between images. So you can understand that, for example, if we want to represent a boat, we can have different representation for the boats. And so here what we want to do is to track not the specific boat, but the concept of the boat into the new image. And what we observe is that if we use segment anything 2 in zero shot, the performance drops significantly. So what we have seen is that SAM2 works really well when objects look alike. So for example, with lungs that are almost similar to each other. But this really struggles when we have high semantic shift. So for example, in the case of challenging dataset like Coco or Elvis. And so a natural conclusion would be that maybe SAM2 does not really understand object semantics, but just visual similarity across images. However, we were not fully convinced about this, because what we observed is that the pre-training of segment anything 2 that consists in tracking an object across frames in a video is really similar to self-supervised learning, which is known to produce semantic features. So for example, in the case of Dino. And so here, our intuition is that the semantic structure is actually there, is just hidden and overlapped with other signals in the feature space of segment anything 2. So I don't want to go too much into the technical details about that. We have a lot of analysis in the paper. So what I would like to tell you right now is that the semantic structure of the feature can be analyzed and can be recovered by means of simple linear projection by training the models on a really limited set of data. So I don't want to go into the details of that, but I want to convince you about this concept. And so I would like to show you the model feature space before and after our adaptation. And in particular, here on the left, I would like to show you some images where you can see that we have some objects. For example, we have two dogs, a lot of people, some frisbee, while on the right we have collected all the objects belonging to a specific set of classes from Coco. And here I'm showing you the feature space of segment anything before our adaptation. And what we are showing here is a principal component analysis where I'm showing the three principal components and the first two principal components. What you can see here is that clearly there is not a semantic structure in the features as the signals are overlapping and mixed together. However, after our adaptation, you can see the emergence of clear semantic structure in the feature space, both in 3D and in 2D. You can see that all the clusters are clustering together, and so we have a clear semantic separation between objects belonging to the same class. In terms of number, we then test our models on a lot of downstream tasks in the context of visual segmentation. And what you can see is that our model is significantly outperforming all the prior approaches, both the specialist models and the models based on foundation models. And what's interesting here is that we are obtaining real high results on the most challenging dataset that is Elvis. Because, for example, if we are just using Coco, here we have just sparse classes. We have to discriminate a dog from a cat, while in Elvis, we have a really challenging setup where we also have to distinguish between fine-grained categories. For example, we have to distinguish a Labrador from a Bulldog. And you can see that here we have a real big gap of more than 10 points with respect to the state of the art. So what's nice about this project is that we are just restructuring the feature space of Segment Anything 2, so you can still use all the functionalities of the original model. So for example, here you can see that we can go beyond the conventional mask for the template, and you can just use a low effort prompt, like for example, boxes or point or scribble. So for example, here you have an example where you can just click on the bus and then the model will be able to segment all the buses in the new image. You can insert point or boxes or scribble, so reducing the cost of annotation, because we all know that collecting pixel-wise masks is really expensive. Also, we test our model beyond objects, trying to see if it is possible to not select an entire object, but just part of the object. For example, here you can see that we tried to prompt the model with just the legs of the dog, and you can see that our model is able to reason at part level and retrieve all the legs and not the entire object. In terms of efficiency, our model is providing the best trade-off at the moment, as we are 3 to 5 times faster, 4 to 5 times smaller, while also providing the best accuracy. So while we have these numbers, the fact is that, as I was saying before, all the prior approaches are mainly building on pipelines where they are solving the two tasks that are feature matching and segmentation with a pipeline where Dino is used to solve, for example, the feature matching part, and SAM is used to perform the segmentation part. While in our model, we are solving all the tasks together in a single unified framework. So this is why we are extremely more efficient with respect to prior approaches. We also test our model in a real world scenario where we used our model to annotate 10,000 images, and we benchmark our model against prior state-of-the-art approaches, and we benchmark these models in terms of segmentation quality and total annotation time. And as you can see, our model is not only providing the best results in terms of accuracy of the annotation, but it's also able to do that in a really short amount of time. So overall, we have our model Sansa that is consistently outperform all the prior works, both at object and part level, while also being the smallest model available. And what's interesting is this is the first solution to fully leverage segment anything without using external feature encoders. So to conclude, what I would like to say is that I think that all this line of research could be analyzed from two perspectives. So from a scientific point of view, we have been the first to systematically investigate the semantic property of the segment anything models, showing that this model is actually able to do a lot of things than just being used as a class agnostic segmenter. But what I think that is the most important part here is the practical usability of our approach. In fact, we are releasing a unified framework that is extremely compact, that is extremely fast, and that can be used in real-world scenario where a user wants to solve a lot of downstream segmentation tasks in a versatile way where the user can decide which type of prompt using, ranging from geometric prompt to semantic prompt like language and visual template. So that's all for me. I don't know if there are some questions.